traveling to St. Petersburg is not possible. So this is really a pity. Stability and control processes are an extremely challenging and exciting topic. As you know, here in Germany, we go for an energy transition of our overall energy system, where we try to move and rely fully on renewable energies. To succeed to this, we need rather long transition time, and especially we rely on sector coupling. That's to say we have to combine electricity grid, gas grid, hydrogen grid, synthetic fuels, heat, and especially also IT services, including security and privacy aspects. And this, when we see Germany as a country in Europe that is closely linked also to Russia, especially via the gas grid, then it becomes very obvious that the coupling of all these sectors in a transnational way, in an international way, is very important, especially as we also have to consider different time regimes. For example, electricity has much shorter time intervals. The gas or heat grid has much longer intervals. And especially when we think of storage devices, there we have to develop completely new technologies and include them in this big energy grid. And this brings me back to this stability and control processes issue that you are going to deal with this conference. In order to be successful in this transition to a new energy system, we need a digital twin that is based on reliable physical modeling. And as the Dean Leon Petrosyan already said, we need reliable and a lot of data that we can use to evaluate our lab scale experiments, our lab scale models, and then to go in the next step to the modeling of the big system. And here, when I look back to the last years, KIT and the St. Petersburg University, we had a lot of contacts. We had exchange of scientists in order to bring together your ideas and our ideas. And I would very much encourage and positively look in the future that we can continue to have mutual visits, exchange of know-how, of models and of data in order to create their joint science. To finish my few words, as we commemorate here Vladimir Zubov, I would also like to remember Vladimir Engelko, who was member of your faculty and who passed away recently. So Vladimir Engelko, he was the personality who introduced me into the extraordinary Russian science, and you will hear a lot at this conference. He introduced me to the great Russian culture and to the interesting Russian people. And that's why I'm so proud to be allowed to speak here. And next time, I hope to join your conference physically. So thanks a lot. I wish you all the best for your conference and a great exchange. Thank you.
Thank you, Achim. Now I think it's my turn to say some opening last words. I hope almost everyone here knows me personally, or at least through email exchange. My name is Anna Golovkina. And at first, I really appreciate you all for attending the conference and especially today our opening ceremony. Unfortunately, this year, global pandemic didn't let us to welcome you in person here in St. Petersburg, making us to shift to the virtual stage. Nevertheless, I thank all of you who, in spite of everything, stayed with us, supported and understood our decisions. Without your contributions, your priceless help with the reviewing process, we couldn't make it. Unfortunately, many participants lost the possibility to see St. Petersburg this beautiful autumn. To make up for it, we will fill the pauses between the sessions with the pictures of our city, along with the songs and poetry by Vladimir Zubov. So what is waiting for us in the next 5 days? 5 invited talks, almost 120 presentations, and I hope lots of fruitful discussions. That's what I have to say about the scientific part of the event. But everyone knows that the major and the most important part of any conference is social interactions and informal meetings. Of course, it's hard to arrange it online, but we still suggest some possibilities. Telegram group with push-up notifications about upcoming events during the conference. Online service, I hope everyone received my mail regarding it. For coffee break meetups between and after the sessions, where everyone can talk with anyone. Round table in the second half of Thursday, and a special session dedicated to the memory of Vladimir Zubov. I encourage all of you to participate actively in the scheduled events, and it's the only way we can traverse this separation. Let's start. So, it's time to welcome our first invited speaker today. It's Professor Noboru Sakamoto, Professor of Science and Engineering Department in Nanzan University, Nagoya, Japan. His talk is dedicated to a dynamical system view on nonlinear optimal control analysis and design. Noboru, are you here?
Yep. Здравствуйте все. Hello everyone, I'm Noboru Sakamoto. Do you hear me well?
Yes,
okay.
Yes.
Thank you. And okay, let me show the screen. Okay. So my name is Noboru Sakamoto from Nagoya, Nanzan University. First of all, I would like to thank Professor Petrosian, Professor Smirnov, and Professor Golovkina for inviting me to this prestigious conference named after Vladimir Zubov. Unfortunately, it's not possible to visit a beautiful city of St. Petersburg, but let's enjoy the conference. So today, I'd like to talk about some kind of unified view using dynamical system theory for nonlinear optimal control analysis and design. I've been working on this nonlinear optimal control field and its application. And this talk is based on the experience and also based on the recent collaboration with a Spanish colleague and also Dutch colleagues, and also, of course, Japanese colleagues on nonlinear control theory. So this is the agenda of this talk. First, I would like to tell what this view really is, what we can really see using this unified view, using dynamical system theory. And next, I will talk a little bit specific dynamical system tools, such as Hamiltonian system, Hamiltonian mechanics, and invariant manifold theory. And next, I will specifically talk about one type of very important optimal control problem, optimal stabilization, which mainly I've been working to apply it for mechanical system control. And also it has relation with the Hamilton-Jacobi theory and the stable manifold. And the second optimal control problem that I would like to talk about is optimal transfer problem, which is related to turnpike theory, which is attracting a lot of attentions recently. And also from dynamical system point of view, the lambda lemma plays a very important role. So the first section is about this view. So with this view, what you can really see is, for example, like this. Let me use this pointer. For example, how on the Y a gymnast does back hip circle using hips and leg motions. Like this. Moment. She uses this reaction of legs to swing up and going up on the high bar. And this is really an optimal stabilization control. And it has a lot of mechanical system control applications. And next thing with this view one can see is why and how central banks manipulate interest rates like long staircase signals. We know that oftentimes like a Federal Reserve or European Central Bank or a Japanese Central Bank manipulates interest rate like this long staircase signal. So they fix or they set a value of this interest and let the economics evolve for a long time. And at certain point, they change this rate very rapidly and fix the next value. This kind of control is called actually a turnpike, and it arises from econometrics. So with this unified view, I hope you will see why these kind of controls are naturally emerge in the optimal control analysis and design. So for this kind of control, people always want to have some certain kind of optimality. Then we get the Hamiltonian system, right? In physics, Hamiltonian system play very important role in analytical mechanics, quantum mechanics. And this equation, Q and P are often used as position variable Q and generalized momentum P. In optimal control theory, we also encounter Hamiltonian system. But this Hamiltonian system does not really have a completely physically meaningful picture. But in our Hamiltonian system, there are two equations. The first one actually represents physical system. And the second one, for a joint variable P, doesn't have a physical meaning, but these are interconnected like this. And actually, this P is related to control, and the control is injected in this physical system, the first part of Hamiltonian system. So we may be able to think this Hamiltonian system as our fundamental equation, like equations of motion, and apply many techniques from dynamical system theory. This is the story of my talk. And next, let me talk more specifically about these tools from dynamical system theory. So for example, Hamiltonian system, Hamiltonian mechanics, and invariant manifold theories are important in this view. For example, volume preservation or energy conservation law, or canonical transformation, Hamilton-Jacobi theory, perturbation theory, maybe Poisson brackets. These are also called symplectic geometry in mathematics. And also important tools is invariant manifold theory, such as stable and unstable manifold, center manifold, Grobman-Hartman theorem, and lambda lemma. And in this talk, I will mainly use these stable and unstable manifold and the lambda lemma. But these are actually playing in a hidden way in the theory, in the development of the theory. So let me talk about invariant manifold theory. Let's consider this ODE, in which linear part is already block diagonalized with respect to real part of eigenvalue. So A is a stable matrix. B has eigenvalues on imaginary axis, and C is unstable. We can always put our any finite dimensional ODE in this form, and this capital X, Y, Z are higher order terms. Okay, and for this system, in 1967, Kelly shows that there exist invariant manifolds, quite a few invariant manifolds. First one is stable manifold, on which X variable is independent and Y and Z are functions of X. On stable manifold, Y variable, a variable for neutral stability, imaginary axis, is the independent variable. On unstable manifold, unstable variable Z is independent variable. And also center stable manifold, center unstable manifold, these kind of invariant manifolds exist in this nonlinear system. To show what is really stable and unstable manifold is easy to use this kind of picture. This is 1 degree of Hamiltonian system, 1 degree of freedom Hamiltonian system with a hyperbolic fixed point, and the flow looks like this, and there are 2 invariant manifolds, red and blue. On this red curve, if you take a solution on this red line or curve, then solution always evolve on this red curve, and they eventually reach the origin, taking infinite time. While on this blue unstable manifold, if you take infinite, minus infinite horizon, then the solution converges to the origin along this blue line. So these are the stable and unstable manifolds. And the computations for several ways of computations exist. This is what we use for optimal stabilization. So this computation uses iterative computation. First, the initial functions are this, so using only the stable functions, and neutral and unstable parts are set to 0, and substitute this in here, and take integration, and take infinite integration here, and also as well integrate infinite interval integration, and define x1, no, x2, y2, k2, and these will be again substituted here and take integration, and we get infinite series of functions, and it can be shown that the limit function of this series converge to stable manifold. We will use this iterative computation in an optimal stabilization problem. Next tool that I would like to explain is a lambda lemma or inclination lemma. So let's consider this nonlinear dynamical system. This F does not have anything to do with control system F. This is a general dynamical system, independent of control theory. But eventually, this F of X will be our Hamiltonian system derived from optimal control theory. But here, this is a totally independent story. Okay, suppose that this dynamical system is hyperbolic, which means that there is no eigenvalues on the imaginary axis. Then, based on Kelly's result, S stable manifold and unstable manifold U exist. S is k-dimensional. Okay, I didn't write the number of unstable eigenvalues is k. The number of unstable eigenvalues is n minus k, an n-dimensional system. And then k-dimensional stable manifold, n minus k-dimensional unstable manifold exists at the origin. And on this unstable manifold U, take any disk B. So disk B has n minus k dimensions, so same dimension as U. So basically some kind of ball in U. Disk does not really mean a complete circle. This is topologically or homeomorphically equivalent to disk, to a circle. That's called a disk. And take any point on S, take any point X on S, and take any n minus k dimensional disk that is transversal to S at X, and take any epsilon, small epsilon, positive. Then there exists a T such that if lowercase t is larger than this T, this disk D transversal to S at X will be mapped by this flow of this dynamical system. And in the image of this D by this flow, we can always find n minus k dimensional disk that is epsilon close to B. But this closeness uses not only the distance, but also the first derivative. So using a C1 norm. It's hard to understand what is really going on. So I draw a simple picture. So this is fixed point, and this is unstable manifold. This is a stable manifold. So take any B in U, and the dimension of B is same as U. Take any B, any place is fine, and take any X on S, and take any disk D that is look like a perpendicular to S, or actually only the transversality is important. the dimension of D is n minus k, same as this U or B. And let this D flows according to the flows of the solution. And then this will be, this disk D will be mapped somewhere here and somewhere here as T goes larger, and somewhere here, and exponentially stretched like this, and exponentially stretched and exponentially squeezed to unstable manifold U. And therefore, we can always find in the image of D by this flow, which is extremely close to this disk B. And this closeness can be evaluated using C1 norm. So roughly speaking, stable manifold theory only tells you how solution behaves on this curve or on this curve. But lambda lemma tells you how solution behaves off the manifold. So this is very important to see what can really happen in our Hamiltonian systems derived from optimal control theory. So using this lambda lemma, we can prove this property. Okay, suppose x equals 0 is the hyperbolic equilibrium of this dynamical system. And then S and U are K and N minus K dimensional stable and unstable manifolds respectively. And take any x0 on S and take any x1 U, then there exists a T0 such that for every T larger than T0, there exists a rho, which can be very small, and y0 in the vicinity of x0. X0 is on the stable manifold, and y1 in the vicinity of x1, which is on unstable manifold, such that this holds. This means that the solution of a two-point boundary value problem has a solution. And moreover, the solution phi of t and x satisfy this inequality. This inequality can be called turnpike-like inequality, which will be very important in a later talk. First, let me show the picture. So there is a stable manifold, unstable manifold. Take x0 any point on S, x1 any point on U, and take any capital T, which is the horizon of this motion, or any large horizon, then we can always find a solution of this dynamical system that connects y0 to y1. So this is really a solution of two-point boundary value problem. And moreover, this inequality, turnpike-like inequality, tells you that quite an interesting behavior of the solution. Okay, this T can be arbitrarily large. So take extremely large T, and okay, substitute this lowercase t, capital T divided by 2, and then this will be e to minus mu times t, capital T divided by 2, right? And substitute this t, capital T divided by 2, then we get the same term here, right? But still this t, which is divided by t, is very, very large, which means that this guy, this term is very, very small, exponentially small, right? which means that this solution is very, very small. And most of the time, this solution stays in a small vicinity or neighborhood around the origin. This tells you how this solution behaves. Starting somewhere here, goes near to the origin and spend a long time here. And at certain point, at certain time, this exits this neighborhood to reach to this destination y1. And if you take a large capital T, this circle rho, the radius of the circle rho should be 0. Because if the horizon starting from here to ending, reaching here is taken very, very large, what you need to find in this 2-point boundary value problem is very, very close y0, very, very close to this stable manifold. So that almost the behavior is almost like stable manifold solution, and goes to the origin, but not exactly to the origin, but stay here for a long, long time and exit. We can do this for any large T. This is the important behavior of this hyperbolic dynamical system. And this can be proven using the lambda lemma. And please remember this name, turnpike-like inequality. Okay, this inequality will be used in optimal transfer problem. Okay, next, let me talk specifically on the first optimal control problem, optimal stabilization. In this talk, I will talk about two optimal control problems, optimal stabilization, optimal transfer problem. In the first problem, the horizon is infinite. And we want to find the control U, overall U, such that the solution X goes to 0 as T goes to infinity. In the second problem, the horizon is finite but large, capital T, but this destination state is designated. So starting from X0, the solution has to end at this XF. This is the second problem. Okay, let me talk on this first problem. So this is a known, very well-known theory. First, deriving Hamilton-Jacobi equation for V, unknown function V, scalar function. If we can find a solution for this Hamilton-Jacobi equation, optimal control is represented as feedback like this. This result is known since the 60s. But the solution methods for this Hamilton-Jacobi equation were very limited. Only several, well, some methods were proposed, but applications were reported almost nothing except for simple numerical examples. In 2008, Van der Schaft and I proposed stable manifold method for this Hamilton-Jacobi equation. And let me talk about that. So this is the Hamiltonian, left-hand side of the Hamilton-Jacobi equation. We wrote dVdx1 P1 using this P variables. And Hamiltonian system derived for this Hamilton-Jacobi equation can be written like this. This A is the derivative of this F. F is this control system. This F comes from this control system. And okay, this represents a first order term, and this is a higher order terms. And we suppose that this Hamiltonian matrix has no eigenvalues on imaginary axis. The important fact which was proved by van der Schaft is the following. Stable manifolds of hyperbolic Hamiltonian systems are Lagrangian submanifolds, which means that they are integrable. So using this, if we can write the stable manifold of a Hamiltonian system with this expression using some p of x, function p of x, then this integrability means that there is a function v of x such that this p of x is actually a gradient of this v. So this manifold is generated by this single function, scalar valued function v. This is called integrability. And actually, this v is the solution for Hamilton-Jacob equation. And the optimal control can be represented like this, using this p. So obtaining stable manifold is almost equivalent to obtaining this optimal feedback. So this picture shows this stable manifold of a simple one-dimensional problem. This hash surface is the stable manifold around the origin. This point here is the origin, and this flat surface is the solution by the Riccati equation. So this stable manifold is tangent to the solution by the Riccati equation. So the application flow of this stable manifold method can be written like this. First, we get the Hamilton-Jacob equation, take a Hamiltonian system, and check the hyperbolicity, and apply the iterative computation that I explained in the tool section, and theoretically use this Lagrangian submanifold property, this integrability of stable manifold. So, and we apply some kind of approximation. Anyways, we need to do some kind of approximate computation. So we approximate this stable manifold P by this pi. And this, using this approximated function pi, our optimal control looks like this. This is the story how to apply this stable manifold method. And we had worked on quite a few applications. And let me show you some experimental result. First one is swing up and the control of flexible inverted pendulum. We also worked on rigid inverted pendulum, of course, but this flexible one is quite interesting. So let me talk about this. So this motivation is from like this kind of space structure, which inevitably flexible due to the light weight. But we want to maneuver this flexible structure in an optimal way, with a fast motion, like agility. Then we need to consider nonlinear optimal control of flexible structure. And this inverted pendulum with the spring steel flexor beam represents this kind of problem. So as you all know, this is a inverted pendulum, but this is flexible beam. And so derive a nonlinear Lagrange equation, which is four-dimensional equation. No, four-dimensional equation, and consider optimal control, which gives you 8-dimensional Hamiltonian system, normal. But okay, let me show you the experiment result. to. I hope video is not enough. So with this simple application of linear control, as we saw, due to spillover instability effect, it gets unstable quite easily. So we append cutoff filter here, one-dimensional cutoff filter, to attenuate the flexible mode. And then we get the five-dimensional system, actually. And consider optimal control, stabilization, which gives me 10-dimensional Hamiltonian system. And we computed five-dimensional stable manifold by iterative method. And we applied this nonlinear. First, we apply linear control with this filter. Okay, then it is smoothly stabilized, right? And next, we will swing up. It's pretty fast, so I hope you can see. This is the slow motion of this swing up and stabilization. So with this, with simple LQ control, the system gets easily unstable. But with this filter, this can be stabilized. And this nonlinear swing up control is slow enough not to destabilize the flexible mode, but fast enough to swing up and stabilize. So this is a feedback of 5 variables. Okay, next, let me talk a little bit about Acrobat swing up. This is similar to the video that I showed at the beginning. Actually, this robot is trying to mimic this gymnastic. Okay, let me show how this apparatus behave. So it's like this is a high bar. This rotation axis here is high bar. And this is a gymnast. And trying to stand upside down on this high bar and using his or her legs or hips to balance at this upright position. This is called the Acrobat system, and it attracts a lot of attention in nonlinear optimal control theory and application. So actually, this system has 4 equilibrium configuration. The easiest one is this down-down mode. And obviously this up-up mode is also one equilibrium configuration, but of course unstable. And actually this first one is up, the second one or leg is down, is also another equilibrium, and the fourth equilibrium is body is down, but leg is up. And most of research on Acrobat is focusing on the swing up control from this down-down mode to this up-up mode. But we apply this nonlinear optimal control theory using stable manifolds for all kind of transitions. And let me show you experiments. This is the one popular in nonlinear optimal control. So from down to up. So as you can see, this control nicely used the leg motion and using this reaction to move this body up. All right. And the next one is from here to here. Using the reaction of leg, nicely go up and stabilize it. And next one is this. This doesn't look so fascinating, but actually this is not so easy, because except for this down, all three equilibrium is unstable. So even this at the first configuration at t equals 0 is unstable. But without falling down, not to fall down the body, this moves, this leg goes into the first in the different opposite direction, so that the body doesn't go down, but this legs is lifted up. And the last one is quite interesting motion. Using this rotation of leg, the body goes up and stabilized. These kind of very nonlinear motion can be stabilized using stable manifold method. Oh, there's another one. Okay, let's move on to the second optimal control problem, which is optimal transfer, starting x0 and go to designated xf. So this comes from econometrics, actually, and it's called turnpike because this theorem tells you that no matter where the initial point of your system and target point of your system locates, the optimal strategy is go to this equilibrium path, which is called Neumann path, and stay there for a long time, and at certain time exit or go to this target point. This phenomena is known to be optimal early econometrics. And the word turnpike comes from this metaphor. So no matter where you are, this is the picture of my city here, Nagoya, in Tokyo, and this line is a highway, turnpike. So no matter where you live near Nagoya, and no matter where your destination is near Tokyo, the best strategy is take a highway and take long miles with best rate. That's the turnpike. This is a quite normal strategy for everybody, and that this kind of control strategy is called turnpike. So, recurrently, turnpike definition of turnpike is written like this. So, for any epsilon, which is normally small, and consider XU space, and take epsilon ball, okay? And this means that the XU, the point XU, is outside of the epsilon ball, right? And this means that the set of T for which this point XU is outside of the epsilon ball is bounded by this yet epsilon, no matter how this capital T is large. Which means that most of the time, because T can be large, but this is bounded. So, and this epsilon, yet epsilon is independent of this horizon T, which means that most of the time, this point XU stays inside of this epsilon ball. So this looks like the hyperbolic dynamical system behavior that I explained using lambda lemma. Okay, the history of the study on turnpike can be summarized in this slide, which I may not have so much time, but please remember this inequality is derived in Boreta and Suasua 2013, and let's call this inequality turnpike inequality. Very similar, right-hand side is very similar to what I showed before, right? And why turnpike is so important? Because turnpike often tells you how to simplify control problems, control systems, like a staircase control signal by central banks. And this simplification does not depend on distance states or horizon length. This is quite important in turnpike. And this turnpike attracts attention in terms in the field of MPC control or optimal shape design or sparse control, which is recently called maximum hands-off control. Which means that like a central bank manipulation of interest rate, once they fixed certain value of control, they hands off. They don't manipulate in a very short period of time. Once they fix, they let the system go without any control, so hands off. So this control, kind of sparse control, maximum hands-off control, have a lot of attention recently for environmentally friendly control strategy. And the mechanism and the conditions of turnpike for nonlinear system is not well known, well understood for nonlinear system when this initial condition and the final destination are large. Okay, this is the problem, and we wish to clarify the conditions on which the optimal transfer problem has a solution that exhibits turnpike. So this is the Hamiltonian system derived from this optimal control problem. And first we'll try to find the solution graphically. Okay, we assume the hyperbolicity of this Hamiltonian matrix. And then we have unstable manifold U, stable manifold S at the origin. And remember how flows behave along or around these manifolds, okay? So, for example, when your initial point is here and destination is here, the strategy you can take is take this P relates to control, right? So take this control value and let this Hamiltonian flow evolves, and then eventually this goes close to the origin, and after that, along this U, the system comes here, and then you get this destination. Okay, if this capital T is large, then the strategy will be going to the neighborhood of the origin and spend a long time here and come here. If this initial point is here and the destination is x1 and capital T is very large, you don't go from here to here like this. Take this control action and go near the origin and spend a long time, and near unstable flow, using unstable flow near U comes to this destination. And then we can prove this theorem using lambda lemma. So assume that linearization is stabilizer detectable, and then US stable and unstable manifold exist. If your initial point is the projection of S to the base space, pi1 is projection, And if your destination is in the projection of unstable manifold U, then plus some technical assumptions, then for large T, optimal transfer problem has a solution which satisfies the Turnpike inequality. We can prove this using lambda lemma. So let me show you one simple numerical example of nonlinear system, a very simple one, very typical cost functional. And I completely omit the computation, but you can show that the unstable manifold has this structure, and this stable manifold S satisfies this condition. This is not so easy, but let me omit the detail. Which means that if you take the destination on satisfying this condition, like xf1 is 0, here, x1 is 0, so xf1 is 0, and take any initial point, because of this, you can take any initial condition. Then Turnpike occurs. This is the figure of the Turnpike trajectory starting from 12, and xf is 0.5, x1, x2, p1, p2, but looks quite weird. Looks quite weird, right? Because starting from 12, but this has almost 200. But actually, if you enhance the initial time between 0 and 0.1, starting from 12, but x1 grows really, really large. But it still shows Turnpike. So Turnpike is confirmed, but in this phenomena, we can see that the nonlinear peaking phenomena, which is quite a problematic phenomena in nonlinear stabilization problem. This is occurring in this trajectory, but it's still Turnpike. So let me summarize my talk. So I try to show a unified view using a Hamiltonian system as a Hamiltonian system derived from optimality condition for nonlinear optimal control as the fundamental equations of motion, and apply nonlinear or dynamical system tools such as Hamiltonian mechanics or invariant manifold theory. And then I consider two types of control problems. For optimal stabilization, stable manifold and its computations play a very important role. We have this kind of Acrobat application and the aircraft control application, and also maglev control with constraints. And the second problem, which is the optimal transfer problem, Turnpike theory is attracting a lot of attention, and using this unified view, using dynamical system theory, specifically lambda lemma, we can have we have a sort of framework that easily understand why a Turnpike phenomena occurs. Спасибо, что вы слушали. Thank you for listening. If you have any question, please ask me, or using chat, or maybe in a different occasion.
Это он сам или другой человек? Он сам, да. So really, I'm not specialist in this field, but my question is, that it may happen that your control will be not admissible. So in practical life, you cannot realize it because there are some restrictions on control variables. Why you don't consider cases when you have this, when you have some restrictions on controls?
Well, yeah, at the beginning, this study was to understand turnpike phenomena from geometric or dynamical system point of view. So we simplified all the situations. So in the next problem, next work, future work, we need to consider such kind of limitations or control constraints. But actually, in the recent work with Professor Nagahara, we consider sparse control. In the sparse control, we consider control limitations. We're using L1 norm. And the sparse control, or a maximum amount of control, is considering the restriction. And we found that still turnpike phenomena occurs in such kind of control. But there are many kinds of constraints which we have not really considered in the future. That will be future works.
Thank you. Thank you. Other questions?
We have one question. Sergei Zavadskiy, as I can see.
Hi,
Yes. Yes, thank you. Can you hear me?
Sure, yes.
Naburo, thank you very much for an interesting presentation. And I'm really excited with your real life examples. It was very interesting. And, you know, I would like to ask you, so am I correct that, for example, for your Acrobot, you have spatial digital processor to stabilize your Acrobot. And in this digital processor, you achieved the only one controller for any initial position of Acrobot.
Well, not really any, but because the control problem is always starting, for example, starting from the pending position, but it needs the robustness. So around the that initial point, it's also swing up and stabilized.
I see. Thank you. So it seems you consider all major initial situation.
Yeah.
Yeah. Thank you.
Okay, thank you. We have one more question. Nikolai Smirnov, please.
Dear Professor, as well known, we usually use sensor for organize feedback control.
Yes.
What do you think about use artificial intelligence instead of sensor? Thinking about this approach, maybe you have an experience or so on. Thank you.
Okay, you mean we also use observer in this experiment because we need to get all the states information for feedback. But we have not really applied artificial intelligence, but it may help in designing more robust control using the data, especially the experimental data. That would be a very interesting direction of research. But for mechanical system control, not much has been done. So that's a very open, and that will be a very active field of research, I think.
Thank you. Thank you very much.
Okay, thank you. Any more questions to our speaker? If no questions, then let's thank you for this great presentation. Yes, unfortunately, we can clap our hands only using this icon in Zoom, but we with Professor Leon Petrosyan has an ability to clap our hands personally here. So it's time to invite our second invited talk today, Professor Alexander Fratkov. He's a professor at Department of Theoretical Cybernetics at St. Petersburg State University, and also he's a head of the Laboratory of Complex Systems Control in Institute for Problems of Mechanical Engineering of Russian Academy of Science, and professor at St. Petersburg National Research University, ITMO. His talk is dedicated to adaptation and learning, a brief history. So if you would be in our normal situation, I would say the stage is yours, but now I can say only the screen is yours. So let's welcome our next speaker.
Yes, now, can you hear me?
Yes.
Okay. Good morning to everybody. And I would like, first of all, to thank the organizers for inviting me to give this talk at this very interesting conference. And now I need to share my screen. Can I do? Yes, I can do that. Okay, now can you see? Oh. Okay. Can you see my screen?
Yes, everything
Yes.
is great.
Okay, I now
But could you please pull it full screen?
full screen, yes, full screen, just a minute. Full screen up. How to Okay, I have a couple of minutes to tune for tuning. Okay.
And in the upper part of your screen, there is a press motor button. You can click there and then choose full screen mode. Or F11 or Control A, for example. Try to.
Control A, no. Not. No. Just a moment. No.
But okay, it's I think it's
maybe if it is
yes, okay, can continue like that. It's okay.
Alexander Lьвович, Control L, L Larissa.
L is for PDF, it's PowerPoint. So I think that's okay. I have made it a little bit extended. Can you see the screen now?
Yes.
Yeah, I think it's enough. So, dear colleagues, let me start my talk. It's actually a sort of interdisciplinary talk between different branches of control theory and artificial intelligence. There are not not much interaction at the moment. And I was thinking recently how to establish some more links between these very important branches. The it is important to look into the history. This may be a key to understand what is going on now, is to understand the history first. Well, saying adaptation and learning is sort of very broad terms, and I will not use these terms in a very broad sense, as you can find in dictionaries. But I would focus only on control science and computer science understanding of these two terms, adaptation and learning. So the outline of my talk is as follows. After a brief introduction, I would like to go in a chronological order to start with the birth of machine learning and its more broadly artificial intelligence. And then I will present you a brief history of adaptive systems. And then we'll speak about early years of adaptive systems and machine learning, which could be called first spring of or golden age of machine learning and adaptive systems. Then it happened that the first winter of artificial intelligence started, then second spring, second winter, then currently in the 21st century, a new era of artificial intelligence started, and deep learning was coming to the stage, and I will finish with some conclusions. Okay, let's start with introduction. Probably most sources say that the history of artificial intelligence started in 1943 when the paper by Warren McCulloch and Walter Pitts was published, where the concept of artificial neural network was first time proposed. And in particular, they proposed a model of an artificial neuron and showed that a network of such neurons can work as a Turing machine. So make a universal computation. And the model of neuron, which is now called McCulloch-Pitts model, is very simple and even simplistic if we speak about biological neurons, because it does not take into account the dynamics of the neuron, like modern models like Hodgkin-Huxley and some other models. But it is important that it is important and very convenient for computation. And, artificial neural networks are mostly using now this model. Note that Walter Pitts at that time was very young, about 20 years old. Next source of development of current computer science and control science was a famous book by Norbert Wiener, Cybernetics. Cybernetics, or Control and Communication, the Animal and the Machine, which was published simultaneously in the US and Europe in 1948. and starting with this book, cybernetics and this area have become very popular among many people, including not only mathematicians and engineers, but also humanitarian. And Wiener started organizing a number of conferences, which were called the MASI conferences, where researchers from interdisciplinary community get together and discussed such new terms like information and feedback in many disciplines, including biology, sociology, ecology, economics, politics even. And these activities was very important for science in general when the computers just came into the stage and nobody knew how to use them. However, in the year 1953, it happened that there was a personal conflict between Wiener and McCulloch, and their interaction stopped. Actually, although McCulloch was working in the lab headed by Wiener that time. And also new people came into the this area, and new activities was going on, and people were needed new flags for further development on the area. For example, such famous researcher as Alan Turing was also interested, and he posed a question how to recognize that machine can think like a human. He proposed what is now called Turing tests, and his famous paper by 1950 was translated into Russian as a book, «Может ли машина мыслить?». And also information theory was invented just at the same time by Claude Shannon. So other people were interested in further development of this area. And then we may try to understand how the artificial intelligence really was born. And machine learning that time was not a part of artificial intelligence. So the birth of artificial intelligence was due to a number of results obtained by different people, like results in logical methods or symbolic methods, for example, translation from one language to other language, symbolic reasoning. Some machine first time obtained some logical results in mathematical logic automatically, and also geometric continuous methods like evolutionary simulation, evolutionary computation, which was born just that time in 1954. And all that resulted in interest in all this in this area, and a new conference was organized by several people: John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon. Actually, it was in the summer of 1956. And at this conference, the area of artificial intelligence was discussed very actively by top research in this area, and the term, the very term artificial intelligence was coined by John McCarthy. So after that, not after that, at the same time, different activities was going on. For example, activities in creating neurocomputers and learning, introduction of learning into this area. Actually, activities started in psychology. The famous psychologist Donald Hebb in 1949 introduced the learning model of learning for neurons, for artificial neurons. And this model was very simple, just change the weights of the neural model proportionally to product of its input and output. And this model was used by young neurophysiologist Frank Rosenblatt from Cornell University. In 1957, he proposed a diagram of a device simulating the process of human perception, called it perceptron. And he got money for creating the machine. And in 1960, the perceptron, the first perceptron was implemented, Mark I. And the model of the perceptron was just a little bit simpler, more complicated than McCulloch-Pitts neural model. It has some associative elements in the middle, one layer of associated elements. Also, in the following books, Rosenblatt discussed more complicated, more complex models like multi-layer perceptrons, but only one layer, single layer perceptrons were implemented really. And they were studied by several people. Now let us jump to the brief history of adaptive systems, which was in parallel. There were no interaction between control science and artificial intelligence at that time, and a number of years afterward. So the start of adaptive system theory is related to the famous at that time MIT rule. The results showing how to tune the gain of controller in the scheme with a reference model. When we have a model of our desired motion, and we have a real plant, and we don't know the gain of the real plant, and we instead can tune the controller gain. And in order to make the motion of the closed loop system close to the motion of a reference model, the MIT rules, so-called MIT rules, was proposed by Whittaker and others, and it's very simple. That's why it became popular. Many people tried it, but sometimes it didn't work, and in real experiments, it was not successful. I quote the later paper by a number of famous researchers, Brian Anderson, even Marils and others, 1987. They revisited the MIT rule, and first time they prove they have found conditions when it works, when it doesn't work. And in the experiments, it were some failures of adaptive system based on this rule. Therefore, theorists were working and tried to improve and this rule and to create new ideas in theoretical way. And the milestone paper was by Patrick Parks in 1966, who proposed to use a Lyapunov method for design of adaptive system, particularly for adaptation algorithm. In a more general multivariable setting for systems with reference model, for linear controller, the adaptation algorithm looks like that. It's quadratic differential equations. Its right-hand sides are quadratic. And this design was very successful because it was regularly justified, and it was rather general, and many people used it and developed it further. And later, even it was extended to nonlinear setting for nonlinear plant dynamics and probably nonlinear controller. Adaptation algorithms can be designed using so-called speed gradient principle if you have a goal function or objective function. You can make can evaluate velocity of changing the goal function along trajectories of the plant, and then evaluate the gradient of the speed with respect to the adjustable parameters. And such a simple construction can be used and is successful because Lyapunov function can be used to prove its convergence. And later it was extended in several directions, particularly just recently Maxim Dolgopolik extended it for not smooth and discontinuous case. By the way, Maxim Dolgopolik was graduated from the Faculty of Applied Mathematics Control Processes of St. Petersburg University, and 2 years ago he got an award like award of St. Petersburg Mathematical Society to young mathematicians, to the best young mathematicians. And a different approach was proposed by Professor Yakubovich, also from St. Petersburg University, in the middle of 60s. And it was based on a discrete time model of the controlled plant. And maybe some nonlinear goal function. And adaptation algorithms proposed by Yakubovich looked a little bit similarly because it's also gradient type, but it was based on an idea of solving inequalities, recursive inequalities, which the initial problem is reduced to the solving of set infinite number of inequalities, and to solve these inequalities, maybe some gradient type methods may be used, and also it was proved by Yakubovich and his co-authors, the results based on the quadratic Lyapunov function. So this approach also was applied to many problems. And now, nevertheless, not all the problems were solved. I just list a number of problems like output feedback control without measurement of the whole state. Usually adaptive observer were used to solve this kind of problems. How to cope with the noise also is a problem. It requires regularization of adaptation algorithm. The problem of taking into account delay in the distributed systems, acceleration of convergence of the method, and so on. But since we are speaking about a brief history, very brief, we don't have time to go into all these problems and all these results. The literature is huge on adaptive control. Now let us come back to machine learning and artificial intelligence. In the 60s, there was the situation like a growth of interest to cybernetics and learning algorithms, pattern recognition. Rosenblatt's results were very popular at that time, and in many countries, including Russia, the Soviet Union, people worked in this. And also other results in artificial intelligence like fuzzy systems and first chatbot were proposed that time in 60s. In the Soviet Union, a number of results in pattern recognition was obtained in Moscow by Bonk and Braverman and Zerman, in Leningrad by Yakubovich and his colleagues, in Moscow also Lerner, Vapnik and Chervonenkis. It's all these results were published in mid-60s. And also in the area of artificial intelligence, results by Dmitry Pospelov, Zakharov, Khoroshevsky, and other people. But these two communities did not interact actively at that time, as in most time. I would like to bring your attention to the paper by Yakubovich, where first time the term machine learning was introduced, machine learning to recognize patterns. It was a paper published in Russian, 1963, in the book published in St. Petersburg, Leningrad University, so it was not very well known. Not many people knew about this publication. And now I would like to present you a view of machine learning by example of recognition of faces, how to reduce this problem of apparently related to artificial intelligence, how to reduce it to what we can relate to adaptive system and learning. So suppose we need to recognize male and female faces. Standard approach is digitization. We introduced coordinates, and we have number of measurements, number of training data, and where we know which faces are male faces, which faces are female faces. Then having these coordinates, we reduce the problem to a geometric problem, to separation of two sets in the Euclidean space. In the simplest situation, these two sets can be separated by a plane, hyperplane. Suppose we have such a situation, the two sets can be separated by a hyperplane, just for simplicity. And we need to find this hyperplane. How to do that? A good way to solve this problem is to jump to a dual space, to the space of weights, coefficients of the hyperplane, and make an recursive algorithm which implements a projection of the vector of weights to the next hyperplane corresponding to the point to the face element of a training data set. And this idea was implemented by Yakubovich in his next paper, and another paper which I mentioned by Yakubovich in the related to adaptive systems. So it's the same algorithm can be used here. And the understanding that same algorithm may be used both for adaptation and for learning was explicitly promoted by Yakov Tsipkin from Moscow, a famous Russian researcher. He published a book in 1968 in Russian. It was translated into English in 1971. The book was exactly entitled as Adaptation and Learning in Automatic Systems. And it's very interesting book. I purchased this book when I was a student, that time in the end of 60s. And I was excited with this book. And I was trying to follow the ideas of this book for many years. And the key point how is in this book is to use the general iterative algorithms for solving uncertain optimization problem to solve different adaptation and learning problems. For example, pattern recognition. This is our chapters. This is a list of chapters of this book. The same algorithms are applied to pattern recognition, to identification, to filtering, to control, to study reliability, operation research, and games. So it looks like the same method can be used for solving quite different, completely different problems. It was very interesting. And it is important even now. This book was published almost more than 50 years ago, actually. And it's important now, still important now. Just a few ideas from this book. The main idea was using algorithms of stochastic approximation. The initial problems was formalized like a minimization of average risk. The loss function is Q of XC, and probabilistic iterative methods was used, which has also gradient nature. And the gains of this gradient procedure should be used in a way in order to ensure convergence of the estimates. More details can be found in the recent paper by Boris Polyak dedicated to centenary of Yakov Tsipkin. It was celebrated last September, and in the IFAC Congress this year, this paper was published. So, what is also interesting in the book by Tsipkin is that he not only introduced the idea of a similarity of algorithms, he even demonstrated how different algorithms used by different authors and published in different papers can be derived from his scheme. And he put the tables into the book, not one, but several tables. And here you can see the names of the authors published in, whose results were published in different papers, but they can be derived from the scheme of Tsipkin. And these authors are Yakubovich and Eiserman and other people, and also Professor Vapnik, who is famous expert in the machine learning famous even now. I will speak about him later. He also, his results, his algorithms also can be derived from this scheme. So after this golden age of 60s, in the 70s, an interest to learning and artificial intelligence was not very strong. It was caused by several reasons. First of them is a publication of the book by Minsky and Pipert, Perceptrons, where the idea of artificial neural networks was criticized. It was shown that single layer perceptron cannot implement the simplest logical function, XOR. And it was like a piece of cold water to people, to researchers. And some other failures were simultaneously happened. Some bad experiments with airplane, and some bad, some not successful Japanese supercomputer project, which was closed, and some other negative results were obtained. For example, the so-called combinatorial explosion of a number of algorithms to solve complex problems was discovered. And, Richard Karp discovered that if number of input data increases, then the time for solving problems grows exponentially for a broad class of problems. This phenomenon was also known under the name of curse of dimensionality, introduced by Richard Bellman, but it was sort of negative. It had all that had a negative influence into the combinatorial logical approach to artificial intelligence. And funding was reduced, and the number of researchers were stopped at that time. That's why it's called winter. After that, however, in the beginning of the 80s, there was a second spring of artificial intelligence, which was caused by a couple of inventions. Production method expert systems were introduced, which happened to be first industry application of artificial intelligence. Also, that time, some theoretical results were obtained first by Fukushima, who proposed convolution networks. And then Paul Verbos was studying multi-layer neural networks and proposed a backpropagation method. Although several other people also introduced something similar to backpropagation method, but it was really, it has become really popular after the works of Verbos in the beginning of 80s. So an interest to artificial intelligence grows again. And however, these expectations were probably too high. After a number of interesting results, obtaining interesting results, not many practical results were obtained, and an interest again went down. And this time is called the second winter of artificial intelligence. Some people think that the main reason for beginning of the second winter of AI was emergence of personal computer at that time, in beginning of 80s, which caused the need for a large number of software products and attracted many developers and researchers in the area to a different branch to personal computers development software for them. Anyway, after some time, again, interest in artificial intelligence growth. It was in beginning of the first decade of the 21st century, and it was a turning point in the history of machine learning too. The reason, there are again several reasons of that. Synergistic effect of three synchronous trends. First, the big data, a number of amount of data became so big that new approaches were brought to the life very rapidly, and the reduction of the cost of parallel computing and memory, and the development of new technologies based on graphical processing, and this market was growing very fast, and the cost of computation costs reduced dramatically that time, and simultaneously new algorithms for training of multi-layer networks were developed, so-called deep learning area, and as a result, machine learning made great successes, and it has become dominating area in artificial intelligence that time, and it gained a lot of new applications. It was first decade of this century, about 10 years ago. And now I would like to mention a few more things, few more important things. The famous vector support vector methods, or support vector machine, which were invented by Vapnik with co-authors, but also Vapnik introduced the idea of this method long ago, in the 60s. It is interesting. He got recently a few awards, a few prestigious awards for these researches, but main results were obtained very long ago. And particularly, the method was become very popular. His paper with Sabina Cortez has now about 20,000 citations in the Web of Science, or 40 citations in the Google Scholar. And his book, Nature of Statistical Learning Theory, is cited more than 85 times. And works by Vapnik are now cited about 200,000 times. Probably he is the most cited researcher in this area of Russian origin. And not many people know that some other methods exist that are can compete with method of Vapnik. They were invented, proposed in St. Petersburg, that time Leningrad, in the 60s by Kozinets, and another method by Malazemov, Demyanov, and Mitchell, 1971. These are also part of history. And coming to the deep learning, also we need to remember that first results related to this area were obtained in the Soviet Union, in Kyiv, by Ukrainian mathematician Ivakhnenko, Alexander Ivakhnenko, and published in a number of papers in 1968. Now, in the middle of the last decade, a critical mass of knowledge in the field of deep neural network was accumulated. And The leader of this area was Geoffrey Hinton, a British scientist who continued his career in Canada. Since 2006, he himself and his colleague began to publish numerous articles in deep neural networks, including one in Nature in the year 2015, which has become really huge, very, very popular. And Geoffrey Hinton himself has now almost 400,000 citations. And his colleagues, senior colleagues, worked together in Canada in different universities and were associated with also huge companies like Google, Facebook, and Microsoft. I mean, LeCun and Yeshua Benjo. So these three persons have become leaders in this area. And actually they live in Canada, and Canada has become a center of development of artificial intelligence now. And finally, their work was awarded by the famous award Turing Prize in 2018. Turing Prize is sometimes called Nobel Prize in computer science. So these three persons were awarded with the famous, with a top prize in computer science. Finally, this is the end actually of the history, of this very brief history, and I would like come to some conclusions. First conclusion is that adaptation and learning were very close to each other in the beginning, and fruitful cooperation between them existed in 60s during first few decades of their history. However, dramatic development of the machine learning during last 2 decades leads to the divergence of the two sister fields, which is an issue of discussion in the control community. Indeed, during the IFAC Congress this summer, which went in a virtual manner, there was a discussion organized, there was a session organized by myself and Fuad Jiri related to the history of adaptive control. And my paper was presented there, and some people were interested, and we organized a sort of seminar discussion. And I realized that people in control community feel that their ideas can be applied in artificial intelligence, in machine learning. And the difficulty is that most part of machine learning has now migrated to computer science field. Only two more narrow areas, iterative learning control and reinforcing learning control, are kept within control field. But we need to make bridges between control science and computer science. It's now very important and perspective. And the final conclusion is that strengthening links between adaptation and learning, including deep learning, would be of mutual benefit to most fields. And this is the end of my talk. Thank you very much for your attention, and I would be happy to answer some questions. Thank you.
Thank you, Professor Fratkov. Do we have any questions? Then I have one question for your presentations. It was a very nice introduction to the history of machine learning and artificial intelligence that are the high of the populace nowadays. I would like to ask, in your opinion, you said that we have to build bridges between artificial intelligence and between control theory, because it's the most prospective way of their combinations and future benefits. But what are the main challenges in order to implement some recent advances of artificial intelligence or machine learning in control theory?
Thank you for this question. Actually, I do not know the answer to this question. There are different opinions. And for example, people in artificial intelligence, many of them how to say, have a understanding of the last century, because the changes, the dramatic changes happened very recently. The deep learning is now, how to say, an important part of this area, but there are not many universities that have top experts in this area. And what now is how to say this, the algorithm which were proposed, they are not discussed in the control community, for example, because in control community people are often interested in justification of algorithms, formulation of theorems, rigorous results. If we compare this way of thinking with what is can be observed in machine learning, in artificial intelligence, they think differently. They have data sets, they have standard benchmark problems, and they compare new algorithms, new ideas by example, by testing them on the data sets. And also acceptable, but it's different way. It's not easy to compare and not easy to make bridges and make cooperation between two areas. There's two big areas of science, control science and computer science, actually, artificial intelligence. So, but my idea is that we need to discuss, we need to meet and to discuss and to try to find new common points of our thinking. We are just in the beginning of this. I think the nearest years will show how to do that.
Yes, thank you. Here I also agree with you, and because nowadays this industry 4.0 is a great challenge everywhere, and everybody is talking how can we utilize the sensor data that we collect in so much quantity in order to use it in our already built control algorithms. So yes, this topic needs to be discussed more precisely between two communities, as well as machine learning community and control theory community. So thank you for this first bridge between these two communities that you tried to build during your talk today. Let's thank our invited speaker for his presentations. Thank you. And here is almost 12, so we can stop our translation now and see you in 2 hours in our sessions. We have 2 tracks today, A and B, and they start at 2 p.m. in Moscow time. So see you there.
Thank you.
Thank you.